Hi, welcome to JEE Chemistry Tutor once again. In the last class, we have seen that the wavelength of all the spectral lines of hydrogen atom spectrum can be calculated from Rydberg's formula, which is 1 by lambda equal to R into 1 by N1 square minus 1 by N2. Now you can see this formula is totally controlled by two integers. Now why should a hydrogen atom care about our integers? And we have seen from the Bohr's theory that these integers are coming from the fact that the energy of the stationary orbit are quantized, and the great success of Bohr's theory was that it can explain the line spectrum of the hydrogen atom. Now this is the first theory which gave an expression for the energy of the orbiting electron, and also we can calculate the radius of the stationary orbit. Now in this class we will see some of the drawbacks of Bohr, or more precisely we will look on some of the facts that cannot be explained from Bohr's theory, and we will also look on some of the experimental and theories that question the validity of the Bohr. If you didn't watch our last 3 lectures, please go and watch it, because all the lectures are interrelated to each other. And if you like our videos, then please subscribe our channel and don't forget to press the bell icon to get the further updates. We have seen that hydrogen atom shows the line spectrum. The origin of the line spectrum can be explained beautifully from Bohr's theory. Now, when this hydrogen atom spectrum was recorded in a high resolution spectrometer, it was found that each line consisted of some closely spaced lines. Now, Bohr's theory said that energy is quantized. The orbiting electron can't take any value. Then the question is, why this fine structure? It could not be explained from Bohr's theory, and this was the one of the drawbacks of Bohr's theory. Then in 1915, scientist Sommerfeld extended Bohr's theory and to explain the fine structure of hydrogen atom. So for this, what he proposed, let's see. He proposed that the electrons are orbiting the nucleus in a elliptical path. But Bohr has proposed that the electrons is orbiting the nucleus in a circular path. And we all know that the circle is a special case of an ellipse, where for the circle, the length of the major axis is equal to the minor axis. So if this is A and this is B, so A is the length of the semi-major axis and B is the length of the semi-minor axis, and the for circle A is to B. So anytime that an ellipse can be converted into a circle. Now for Bohr's theory, we have seen that the energy of nth orbit can be calculated from the formula 2 pi square m into the power 4 divided by n square h square, where n is coming from the fact of quantization of energy. So n is quantum number and it is called as principal quantum number. Now the question is, did Sommerfeld just say that orbit will be elliptical? It is no. It can be shown mathematically for a central field problem like hydrogen atom problem. If the energy is negative, then the paths will be elliptical. I am not going to the details of the mathematical calculation. And from Sommerfeld relativistic theory, the energy of an hydrogen atom is En equal to minus 2 pi square m e to the power 4, that is n plus k, that whole square into h square, where k is another quantum number along with the principal quantum number A, and it is called azimuthal quantum number. And it can be mathematically shown that the relation between the principal quantum number and the azimuthal quantum number n by k is equal to the A by B. So length of the semi-major axis by length of the semi-minor axis. And the relation between n and k is following. For a particular value of n, k can take any value between 1, 2, 3, n. Now, for if n equal to 1, then k have only one value. So, k equal to 1. So, in that case, n by k is my 1 equal to a by b. So, it implies that a equal to b. So, this is the special case of the elliptical orbit. So, here the orbit is a circular orbit. Now, if my n equal to 2, so k can have value 1 and 2. Now, when k equal to 1, so my n by k, that is 2 by 1 equal to a by b. So, my a equal to then 2b. And when k equal to 2, my n by k equal to 2 by 2 equal to 1 equal to a by b. So, a equal to b. So, in this case, we will get the circular orbit, and in this case, we will get the elliptical orbit. So, this is for n equal to 2, k equal to 2, and this is for n equal to 2, but k equal to 1. Now, another case when that n equal to 3. So, now k can have value 1, 2, 3. Now, when n equal to 3 and k equal to 1, in that case, my n by k equal to 3 equal to a by b. So, this implies a equal to 3b, and so this is also an elliptical pathway, and n equal to 3, k equal to 2, n by k equal to 3 by 2 equal to a by b. In that case, a equal to 1.5b, but when n and k equal to k are equal, then my a equal to b. So, this is in this case, we will get also one circular orbit. So, this is for my n equal to 3, k equal to 3, and this is n equal to 3, k equal to 2, and n equal to 3, k equal to 1. And this is named as that this is S orbit, this is sub orbit, and this is P orbit, and this is D orbit. So, for n equal to 3, we can get 3 sub-energy levels. And here is the one point is, don't confuse this orbit with orbital. Here, orbital is a 3-dimensional thing, but orbit, it's a 2-dimensional thing. So, what Sommerfeld theory gives an sub-energy level. So, if I say that this is Bohr theory, n equal to 2 and n equal to 3, and if I go to the Sommerfeld theory, then my energy levels will look like this. So, this is for n equal to 2 and n equal to 3. So, from this theory, we can explain the fine structure of the hydrogen atom. This is the great success of Sommerfeld extension to the Bohr theory, that it can explain some of the facts like the fine structure of the hydrogen atom. Let's see some other facts that also question the validity of Bohr's model. Now, we will look on those. To describe the nature of light, scientists always face it, because in some experiments like the interference experiment, light behaves like a wave. But we have seen in the last class that in photoelectric effect experiment, light can show the particle character. So, it has both the wave character and the particle character, and it varies from experiment to experiment. Now, these things can be compared with a visual metaphor. Now, in this picture, you can see two images. One time you can see as a old witch, and another time you can see there is a young lady. The crucial feature of this figure is that these images are not the two halves of the two images, but this is drawn in oneness, and it is the visual perception interaction. Because of that thing, we observe two images in one figure. It is the same as for the light. It is the same entity which we used in the interference pattern experiment and which we used in the photoelectric experiment. It is the same light, but in one place it has a wave-like character, and in one place it has a particle-like character. This disparity of light, that wave and particle, is called wave-particle duality. Now in 1924, French scientist De-Brogile said that if a light can show that wave-particle duality, then why a matter not? What De-Broglie said that the matter which shows a particle characteristic under certain circumstances, it can also show a wave-like character. So a matter can also be shown a wave-particle duality. This sounds strange, but if it happens, then it shows a nice symmetry in nature. And De-Broglie was able to put his idea in quantitative manner. So according to Einstein, in his relativity theory, he proposed a relation between the wavelength of photon and the momentum of the photon in such a way that lambda is h upon p. Now what De-Broglie argued that the matter and the photon both obey this relation. And for a matter, p equal to m into v, where m is the mass of the matter and v is the velocity. So now my lambda equal to h by m. So this is the De-Broglie wavelength of matter. So this is my De-Broglie wavelength of matter. So according to De-Broglie, any matter can show the wave and also as well as the particle characteristic. Now let's see that calculate the De-Broglie wavelength for a cricket ball having mass of 100 gram traveling with a velocity of 90 miles per hour. Now first what we have to do, we want to calculate the De-Broglie wavelength for this cricket ball. Now the velocity is 90 miles per hour. Now 1 mile is equal to 1610 meters and this is 3600. So around it will be 40.25 meters second. Now my lambda will be h by m into v and my mass equal to 100 gram. So it's equal to 0.1 kg. So my p equal to 14.25 into 0.1 equal to 4.025 kg meter second. So now my lambda equal to 6.626 into 10 to the power minus 34 by 4.025 kg. So lambda it's becoming, it will be almost 1 in point something into 10 to the power minus. This is a ridiculously small. This is very small quantity. The wavelength or the matter wave for the cricket ball is very small. Now if we see for a subatomic particle like one electron, where that here it is asked to calculate the De-Broglie wavelength for electron which is moving at 1% speed of light. So my velocity is now 3 into 10 to the power 8 into 1 by 100. So equal to 3 into 10 to the power 6 meter second inverse, and we know that the mass of electron is 9.1 into 10 to the power minus 31 kg. So my lambda is 6.626 into 10 to the power minus 34 divided by 9.1 into 10 to the power minus 31 into 3 into 10 to the power 6. So it will become 0.243 into 10 to the power minus 9 meter. So this is equal to 243 picometer. Now you can see that this is in an atomic dimension. And if we recall the wavelength of the X-ray, the wavelength of the X-ray falls in the picometer region. So the wavelength of the matter wave of electron is as of the same of the X-ray wavelength of the X. In the previous example, for the cricket ball, the De-Broglie wavelength doesn't have any meaning. But for an electron, the De-Broglie wavelength corresponds to the wavelength of the X-ray. So it is clear from these two examples that for the subatomic particle, the wave characters is prominent compared to the macroscopic world. Now let's see some of the experimental verification of this wave character of the electron. When a beam of X-ray is directed to a crystalline substance, the X-ray diffracted in a definite manner, which shows the characteristic features of the atomic structure of the crystalline substance. If X-ray fall on an aluminum foil, the X-ray diffraction pattern looks like this. This is occurring because the interatomic space in the crystalline substance is same as that of the wavelength of the X-ray. Now instead of X-ray, if a beam of electrons are directed towards the crystalline substance, then the diffraction pattern looks like this. So from these two examples, it is clear that the two patterns look similar. And we have seen in the last case where we have calculated the wavelength of the electron, it is the same as that of the X-ray. And this experiment also shows that the diffraction pattern of electron looks like same as that of the X. So we can say that the electrons can also show the wave character. And we have taken this picture from the book of Quantum Chemistry, Donald McQueen. Now, one of the interesting asides of this wave particle duality of electron is that it was the J.J. Thomson in 1895 who said that electron is a subatomic particle, who also calculated the charge by mass ratio of the electron by taking electron as a particle. But it is G.P. Thomson in 1926 who showed for the first time that electron can also show the wave characteristics. And these two Thomson, J.J. Thomson and G.P. Thomson, they were father and son, and they both won the Nobel Prize for doing the research on electron, one for showing the particle characteristics of electron and one for showing the wave characteristics of the electron. So far, we have seen matter both have the wave particle duality. Now, we want to do one measurement of locating one electron. If we want to locate an electron within a distance of delta H, then we should use the measuring device in such a way which has the spatial resolution delta X less than delta X. Now, one of the way of achieving this is using the wavelength of the photon is compared to the delta X. So lambda should be nearly equal to the delta X. So this my photon is coming, and to locate the electron, this photon should interact or collide with the electron, and then it will radiate, and here will be one detector that will detect. During this collision, some of the momentum which can be calculated from h by lambda, which can be calculated from the formula h by lambda, should be transferred to this electron. If there is no collision or there is no interaction, we can't see the electron. Now, if we want to measure locate the electron with more accuracy, then my lambda, wavelength of the photon, should be small. Now, if lambda becomes small and lambda is inversely related to the momentum of the photon, so in that case, the momentum will be great. Now, to locate the electron, the momentum of the photon should some part of it should transfer to the electron, and since the momentum of the photon is great, so the momentum of the electron will also be great. A careful analysis of this experiment was carried by Heisenberg in 1920. He showed that it is not possible to determine exactly how much momentum is transferred to the electron. This difficulty means that if we wish to locate an electron with an accuracy delta H, then there should be the uncertainty in the momentum of the electron. And it can be shown that if delta P is my uncertainty momentum, then delta X into delta P should be greater or equal to 8 pi, or this means 8 by 2 pi. Now, so this is a fundamental property. The uncertainty is a fundamental property, and this relation is known as Heisenberg's uncertainty principle. And this uncertainty doesn't stem from pure measurement or experimental technique, but it is a fundamental property of the act of measuring it. Now the question is that in our daily life, why we didn't experience such behavior? This can be understood by taking the example. Here also we are taking the same example as we have taken before, where the calculated uncertainty in the position of a cricket ball thrown at a velocity of 90 miles per hour, where the uncertainty in the momentum will be 1 millionth of 1%. Okay, so we have seen before that our momentum was 4.025 kg meter second. So our momentum P was 4.025 kg meter second, and the uncertainty will be 1 millionth of 1%. So delta P will be 4.025 into 10 to the power minus 8 kg meter second, and so delta X into delta P, that is equal to 8 by 2 pi, and so delta X will be 86.626 into 10 to the power minus 34 divided by 2 pi into delta P is 4.025 into 10 to the power minus 8. So if we calculate this, it will be in the order of 10 to the power minus 34 minus 20 minus 8, so 10 to the power minus 26. So the uncertainty for this macroscopic world, it is very small, 10 to the power minus 26 meters. Now let's see what happens to a subatomic particle like electron. So here we want to calculate the uncertainty in velocity. If we want to locate an electron inside an atom with uncertainty and position is approximately 50 picometers. So here my delta X is 50 picometers, or if we transfer it to the meter, so 50 into 10 to the power minus 12 meters. Now we have known that mass of electron is 9.1 into 10 to the power 31 kg. Okay, we want to calculate delta V. So from the Heisenberg uncertainty principle, delta X into delta P should be equal to h by 2 pi, or my delta P should be 6.626 into 10 to the power minus 34 divided by 2 pi into 50 into 10 to the power minus 12. This and delta P is m delta V. So now delta V should be equal to 6.626 into 10 to the power minus 34 divided by 2 pi into 50 into 10 to the power 12 into 9.1 into 10 to the power minus 31. So it will be in the order of 10 to the power 10 to the power 34, 31, so 10 to the power minus 3, 10 to the power. So it will be in the order of 10 to the power 7 meters second. So you can see the uncertainty. There is a huge uncertainty in the measurement of the velocity. So these two examples show that although Heisenberg's uncertainty principle is of no consequence for our daily life in our macroscopic world, but it has very important consequences to the atomic and subatomic particles. Now let's look back to Bohr's theory. But Bohr's theory says that, and it has given an expression for the radius, that n square h square by 4 pi square m square. And from the quantization of angular momentum, you can calculate the velocity also. So for a particular orbit, you can calculate the radius and the velocity together. But what Heisenberg's uncertainty principle says that you can't measure the position and the momentum and the velocity of any particle without the uncertainty. So there will be uncertainty in the measurement of the position and the velocity. Bohr's theory cannot explain the Heisenberg's uncertainty principle, and this is one of the drawbacks of Bohr. So we need one more theory that will include the Heisenberg's uncertainty principle. That also we will look on, and how Schrodinger's wave equation considers the wave-particle duality and the Heisenberg uncertainty principle. But in the next class, we will discuss some of the mathematical problems and some of the questions that have been asked in the previous years in different exams. We will discuss those things in the next. Till then, bye.